The goal of this video is to talk about the basics of solutions, including dissolving and concentrations and dilutions. And the first thing to know about solutions is that they are a homogeneous mixture. Which means that they are mixed on a molecular level. And there are two main components of a solution. There's the solute, which is the substance dissolved in another. And that means it's the smallest component. And then the solvent is the substance which is available in a larger amount, and the solute dissolves in it. So as you change the amounts of the solute and the solvent, the actual identification of them could change. But together, a solute and a solvent make a solution. And it is also possible to have more than one solute in a solution. And specifically, an aqueous solution is a solution where the solvent is water. And those are the most common solutions that we discuss in chemistry. All right, now as far as dissolving processes, what do solutes do in water? In order to answer this question, we divide them into two categories, ionic compounds and molecular compounds, because they do different things. The ionic compounds, such as sodium chloride, in water will separate into ions. So it becomes the sodium plus ion and the chloride anion. Whereas most molecular compounds, such as methanol, in water do not separate into anything. They just stay whole, they stay intact, so it's still methanol, but it is now an aqueous form of methanol. All right, and the two ions in an ionic compound, or two ions in sodium chloride, get what we call hydrated by the water. So they separate in the water, and the water molecules solvate around them such that the negative part of the water, the oxygen, faces toward the positive ion, the sodium. So you'll have waters around the sodium, and you'll also have waters around the chloride, but since that's negative, the positive part of the water gets attracted to that. So you still have H2O, but they face different directions depending on whether there's a positive ion or a negative ion. All right, so again, ionic compounds separate into ions. Now sodium chloride separates into two, but other ions will separate into however many components they have. When ionic compounds dissolve and separate into ions, we say that they are an electrolyte solution. All right, so for example, potassium nitrate, it has a polyatomic ion which stays intact, so it separates into a K+ and the nitrate anion. And aluminum chloride separates into its ions. The aluminum becomes Al3+, and then the chlorides are each separate anions of Cl-, so you get 3 Cl-, which means you have a total of 4 ions for each ionic compound formula unit in aluminum chloride. All right, so that's what ionic compounds do. They separate into their ions in water. The molecular compounds, we said most of them do not separate. So when you put methanol in water, you'll get a methanol molecule, and you'll get water around it, but there's just one. There's just the one methanol. It doesn't separate into anything. Okay, so they do not separate. And examples of those are sugars. Sugars don't separate like glucose or sucrose. Also alcohols. Another example it's commonly used is urea. And so these are non-electrolytes. But you'll notice I said most molecular compounds. There is a category that's an exception, and that is acids. Acids are a molecular compound that does separate in water. Okay, and specifically an H plus separates from whatever other parts there are. So for HCl, separates into an H plus, what's left over is a Cl minus. There are some acids that separate but not quite so strongly. HF is an example, so I use a double arrow backwards and forwards on HF, which is weaker because it does make H plus and F minus, but only to a small extent. So acids are electrolytes, unlike the other molecular compounds, and some are weak and some are strong. But this video won't address strong and weak acids very much. All right, so let's have you try writing in similar notation to what I did on the last page, what happens to each of these different species, these 6 different species, when you put them in water. What do they form? So stop the video and try to do your arrows, such as this. Okay, and you put what it turns into, and then check again. So sodium fluoride, that's the sodium atom and the fluoride anion. And then we're also supposed to say whether it's an electrolyte, and if it separates into charged species, it's an electrolyte. So that is an electrolyte. Sodium hydroxide, that will become sodium plus, and hydroxide is a polyatomic ion, so it stays intact as an ion. So that is an electrolyte because we make charged species. Urea, this is the formula for urea. You'll notice that's a molecular compound. It's all nonmetals, and none of them is ammonium, which would indicate it's an ionic compound. So this is urea. It simply stays urea in water. Again, it would be aqueous urea, but it stays intact. It is not an electrolyte. There's no charged species. All right, how about lithium sulfate? Notice there's 2 lithiums there, so you get 2 Li pluses, and you get sulfate, 2 minus. Magnesium nitrate forms magnesium 2 plus, and 2 nitrate groups. And finally, ammonium chloride, that is all nonmetals, but you should recognize NH4 as the ammonium polyatomic ion, so that makes NH4 plus and Cl minus. Now let's talk about solution concentration. So now we'll talk about solution concentration, and the most common units we use for solution concentration is molarity, which is given by the capital M, and that is equal to the moles divided by liters. And moles of what? Moles of the solute. And the volume, liters, is of the solution. Okay, it's not of the solvent. It is the solution, so it's important to remember that when you are preparing solutions, as we'll see. So now we'll go down to making solutions. Now suppose that you want to take 0.5 moles of sugar and add water to the 2-liter mark. What will the concentration of that solution be? So we use a volumetric flask like this, which is calibrated accurately to 2 liters, and we'll calculate the concentration of sugar. Okay, so the concentration is, as we said, molarity, moles per liter, so moles of sugar, 0.5 moles of sugar, divided by the liters of solution, and once we've filled that up to the 2-liter mark, we will have 2 liters of solution. and do the division, and you'll get 0.25 molar sugar. All right, so it's important to know that you don't add 2 liters of water to make this solution. You add water up to the 2-liter mark, and that is again because the denominator is the liters of the total solution, not just the solvent. You can't just add that much water to it. All right, now so we calculated that it's 0.25 molar sugar. Well, what if you want a solution that's 0.25 molar sugar? How do you determine that what you need is 0.5 moles, and how do you measure that? Because you can't measure moles of sugar. So let's say we know that we want that concentration, 0.25 moles of sugar. What we do is we realize that the molarity times the volume is going to equal moles. All right, so the molarity we want is 0.25 molar, and the volume that we want is 2 liters. We multiply those together. When you remember that molarity is moles per liter, and you multiply that by liters, you'll see the liters will cancel and you'll get moles. And in this particular case, you'll get 0.5 moles, which is how we determined we wanted that many moles of sugar. However, you can't measure moles of sugar. What you can measure is a mass, so we have to convert that to mass. And the conversion from moles to mass is the molar mass. So we take 0.5 moles of sugar, and we multiply by the molar mass for sugar, which I'm going to give to you, 342.3 grams of sugar per 1 mole of sugar. We'll cancel the moles of sugar, and the amount we need to measure is 85.6 grams. Okay, which that we can do on a balance. All right, so see if you understand these calculations by trying one of your own. What mass of KCl is needed to make 100 milliliters of 0.05 molar KCl solution? So give that a try. In order to do this, you're going to need the molar mass of KCl, and I haven't given you that one, so you have to figure that out first. The molar mass of potassium, 39.1 grams per mole. Molar mass of chlorine is 35.45, so there's one of each, so together you get 74.55 grams per mole. We're going to need that number. But first, we're going to figure out the moles by multiplying molarity times volume. But remember, molarity is in liters, this is in milliliters. We have to keep that in mind. So we take molarity, we multiply it by volume, but that volume needs to be in liters, so we convert it. Okay, 1,000 milliliters per 1 liter. And then we can multiply by the molar mass we got, which is 74.55 grams per 1 mole. And do the math, and you'll get 0.37 grams of KCl that we need to measure in order to make up the solution that we specified. Let's talk about making solutions by diluting other solutions. So sometimes you make a solution by dissolving one substance, which you probably measured on a balance, into some volume of another solution. But other times you already have a concentrated solution and you want a certain concentration of it that is more dilute. So that's what we're talking about now. So for example, the most common solvent is water. So to make dilutions, generally you are adding water to make a less concentrated solution. All right, and when you do that, it turns out that we do calculations that show us that the number of moles of solute don't change. Okay, so for instance, if you make a solution of sugar in water that is concentrated, but then you add more water, you still have the same amount of sugar, it's just more dilute. All right, so because of that, we have this dilution equation, which is in the box, which shows that the molarity times the volume for the concentrated solution is equal to the molarity times the volume for the dilute solution. And you may remember that molarity times volume is equal to moles. So molarity times volume equals the number of moles of solute when it's concentrated, and molarity times volume in the dilute solution equals the number of moles of solute in the dilute solution. But again, the number of moles don't change, which is why they are equal to each other. All right, so we'll use this to do some calculations. Let's say that we have a solution. We want to know what volume of a stock solution of 2.05 molar copper nitrate is needed to prepare 750 mils of 0.8543 molar copper nitrate, copper 1 nitrate. All right, so we know that we have a stock solution with this molarity, and we're asking what volume. So the concentrated molarity is 2.050 molar, and the volume is what we don't know. So we'll simply write V concentrated. And what we want to prepare is this volume of this molarity. So we'll do molarity first, 0.8543 molar, and the volume needs to be in liters if we want to have our answer in liters. So we'll convert it to 0.7500 liters. All right, then you solve for the concentrated volume by dividing both sides by 2.05 and multiplying these other two numbers, and you'll get an answer of 0.3125 liters. So in other words, about 312.5 milliliters of concentrated solution is needed to make that dilution. Now, another thing to let you know is this equation up here is often simplified by saying M1V1 equals M2V2, where 1 can be the concentrated or dilute, and 2 can be concentrated or dilute. All right, now it's time for you to try an example. 40 milliliters of 3 molar HCl is diluted to 100 milliliters. What's the new concentration? All right, so in this case, what you don't know is a concentration. So the unknown is actually the concentration, the molarity of the dilute. All right, so we'll do our molarity concentrated times volume concentrated equals molarity dilute times the volume of the dilute. All right, and what we don't know is the volume of the dilute. But we do know the concentrated solution. That's this one. So the molarity is 3. The volume is 40 milliliters, which is 0.04 liters. And the new concentration we don't know, but we know that it's diluted to 100 milliliters, so that's the volume. So our unknown is the dilute molarity. The volume is 0.1 liters. And if you solve for the molarity of the dilute, which I'm abbreviating as just D, you'll get 1.2 molar. So remember that any of these 4 variables in this equation can be solved for as long as you know the other 3 in a dilution calculation.